this final section, we're going to walk through a guided inquiry exercise that further details what we've talked about in the unit. So let's find the amount of iron in steel wool. Steel wool is often made from an alloy known as low-grade carbon steel, an alloy containing only iron and carbon. This exercise will guide you in devising an experiment to determine the mass percent of iron in a sample of steel wool. The first step in this, and most experiments you will design, is to answer the question, what parameters will you need to measure? So think about that, and then we'll move through the next slides to discuss it. All right, so did you come up with these parameters that you would need to measure? You would need to measure the mass of your initial steel wool sample, and you would need to measure the mass of the iron in the steel wool sample. Finding the mass of the steel wool is easy, but how do you find the mass of the iron? This will turn out to be a long process, so think simply, what do you need to do first before you can find the mass of the iron? Okay, so what you need to do first before you can find the mass of the iron is separate the iron from the steel wool. Go back through the separations topic and identify what method would you use to separate mixtures of solids. All right, so if you reviewed that separations topic, when dealing with alloys, mixtures of solids, the only way to separate components is by using a chemical reaction. So here's what I've shown. Nitric acid is often used to remove certain metals from mixtures. Nitric acid will react with the iron according to this reaction. If we react the iron in the nitric acid, we get this iron nitrate, NO, and 2 waters. Now we'll have an iron nitrate solution, right? What can we do with that to find out how much iron was in the steel wool? So if we put the sample of steel wool into a nitric acid solution, the iron will dissolve into the solution and then we'll have iron nitrate. Now what do we do? What do we do when we have an ion dissolved in the solution? Go back and review that spectrophotometry topic. So once that iron 3 ion is dissolved in the nitrate solution, iron 3 is one of the ions listed in the table of ions that produce solutions with a color. It is typically orange in color, similar to a rust. We could measure the concentration of the iron 3 ions using a spectrophotometer. Remember, we want to end up with the mass of iron in the steel wool. If we find the concentration, how will we transform that concentration information into mass? What additional information will we need to know and or measure in addition to the concentration? Think about it, discuss it with your group if you have one, and then we'll go ahead and go over it on the next slide. So the question was, how do we transform the concentration that we find through spectrophotometry into the mass? Well, since molarity is moles of solute divided by liters of solution, we would need the total volume of our iron 3 nitrate solution. Once we get the concentration, we can use the volume to find moles of iron 3 nitrate. Of course, from there, we know that for every mole of iron 3 nitrate, there's 1 mole of iron ions, just based on the chemical formula. And then for every mole of iron ions in the solution, there was a mole of iron in the steel wool. All that is left to do is to convert to grams using the molar mass of the iron, and then we can find our percent mass of iron in the steel wool. So now that we have some idea of how to accomplish our goal, what are some of the actual steps we would perform in the lab? Again, think about this, talk with your group. We'll discuss on the next slide. So here's how we might carry out our steps. First, measure the mass of the steel wool sample, our starting mass. React that steel wool with concentrated nitric acid, a known concentration of nitric acid, until all the solids are gone. Do this in a fume hood. The NO gas formed in this reaction is highly toxic. Dilute the resulting solution with distilled water to a known volume, such as 100 milliliters. Prepare the iron 3 nitrate solutions of known concentrations and a distilled water blank. Measure the most concentrated solution to choose the optimal wavelength, and using the optimal wavelength, measure the absorbance of the blank and make sure it is 0. From there, we measure the remaining standard solutions and graph the standard curve. Measure the sample from the reaction between the steel wool and the nitric acid, and use the standard curve to convert the absorbance of the reaction sample to a concentration. Calculate the moles of iron 3 nitrate, the moles of iron in the steel wool, convert that to grams, and then find the mass percent of iron in the steel wool. So those 12 steps summarize the discussions we've had previous to this that you would want to carry out to be able to accomplish your goal. So here are some post-lab questions we might expect to see if we gathered all that data that we talked about in the previous 2 slides. So a student performs this lab and did not use the optimal wavelength to measure absorbance of standard sample and experimental sample. Will this introduce error into the result? And if so, describe the error and explain your answer. Do some research beyond this presentation before answering, and then I'll advance to the next slide to review. An argument can be made for either answer, yes or no. Will this introduce error into the result? It is the defense of the answer that matters most. First, let's look at the answer, yes, it will introduce error. With a spectrophotometer, the amount of error may not be the same across a range of concentrations. Using the optimal wavelength makes the measurements of the smaller values far more accurate. For samples with small concentrations, using a wavelength other than the optimal one would introduce a significant amount of error. Multiple readings of the same sample would not be consistent or repeatable. So we talked about that. When we're on the extremes, extreme high, extreme low concentration, we don't get consistent or repeatable results. And so if that were the case of our solutions, we would have some error. Now, let's look at the answer, no, it will not introduce error. There are several situations where this would be true, and it would actually be more accurate to use a wavelength that has high absorbance, but not the highest. These situations are listed below and explained on the next slide. Scenario 1. There are multiple wavelengths with high peaks that are all about the same intensity. Scenario 2. The wavelength with the highest peak has an absorbance greater than 1. Again, we had talked about that. We want to keep that wavelength below 1 to get repeatable results. Below are the conditions under which using a wavelength other than the wavelength with the highest absorbance would be more accurate. In that first scenario, there's unlikely to be any difference in accuracy in using one or the other of multiple peaks. You could check if both give equally consistent results, then which one is used does not matter. In the second scenario, using a peak with an absorbance greater than 1 as the optimal wavelength can reduce the precision of the spectrophotometer and reduce the linearity of the standard curve. Either scenario would contribute to non-repeatable data and inaccuracies that could not be corrected with calibration or nonlinear curves. Post-lab question 2. Why is it necessary to dilute the reaction solution to a known volume before measuring its absorbance? Choose one of the below answers and explain your choice. 1, to dilute the concentrated nitric acid that was used. 2, to have a known volume so that the moles of iron ions can be calculated from the concentration. 3, to have a sample with a lower concentration to measure. Or 4, it is not important to dilute the reaction solution. So you could go back through the experimentation part previously and see if you can't narrow it down here. Discuss with your group, come up with something, and we'll talk through the answers on the next slides. Okay, so choice 1, to dilute the concentration of the nitric acid, is not correct. Most of the acid reacted with the iron and there would be little left over. Choice 2 is correct, but not the best answer. So it is true that We want to have a known volume so that the moles of iron ions can be calculated. The known volume is important. However, the student could just measure the total volume of the reaction solution. Choice 3 is correct, to have a sample with a lower concentration to measure, and it's the best answer. After the reaction, the concentration of iron 3 ions is likely to be very high, which would give the solution a very deep color. Measuring the absorbance of such a solution would be inaccurate. We're talking it would be on the extremes of that standard curve. Choice 4 is incorrect. Dilution is necessary for that above reason. Post-lab question 3. Why is it necessary to continue to add nitric acid until all of the solid steel wool has disappeared? Again, look back through the previous slides, talk with your group. We'll discuss on the next slide. In order to successfully complete this lab, nitric acid needs to be present in excess because it is important that all of the iron in the steel wool sample reacts. Acid should be added slowly, 1 milliliter or so at a time, allowed to react, and then visually inspected for remaining steel wool. If some of the iron does not react, then it will be impossible to get an accurate percent mass of iron in the steel wool sample. The amount of iron in the sample determined will be less than the actual amount if we don't add that nitric acid in excess. Post-lab question 4. A student performed the standard curve and obtained the data below. Then he continued with the lab following the procedure carefully. When he compared his results to a classmate's, they were not similar. Assuming the classmate also followed the procedure accurately, whose results are inaccurate and why? Shown is data for the standard curve, concentration, and absorbance. Try to think through this on your own first, and then we'll go to the next slide and discuss. So the classmate may have accurate results. This student did not record the standard data correctly, obviously swapping absorbances for the 0.2 and 0.3 molar samples. The student failed to note these as outliers while doing the standard curve, causing the slope of the best fit line to not be representative of the data. If those 2 points were removed or the data was regathered, the results would have been more accurate, possibly even close to those results of the classmate. Post-lab question number 5. Below are accurate standard curve data. The absorbance for the properly diluted to 100 milliliter reaction solution and the mass of the steel wool sample. So, make a standard curve graph and find the slope of the best fit line. Calculate the molarity of the reaction solution. Calculate the moles of iron 3 ions and moles of iron in the sample. And finally, calculate the mass percent of iron in steel wool. So this is some sample data. This is our standard curve data, the mass of the steel wool, and the absorbance of our unknown reaction sample. Let's go through each part together. Okay, so here is the standard curve, the graph. So we plotted our data for absorbance and concentration, drew a best fit line, and finding the slope of that best fit line, which you can see in the equation here, 1.3897 is our slope. Okay, let's calculate the molarity of the reaction solution. So remember that molarity of the reaction solution is the concentration. We simplify Beer's law to match our variables and equation where this m is the slope of the line, A is the absorbance that we measure of our unknown, and we can use that to find the concentration. So the plus b part of the equation is omitted. It's close enough to 0. In theory, the line should go through the origin, but of course we're talking about experimental data, so it's not perfect. So let's rearrange to solve for concentration. So we take our measured absorbance, 0.517, and divide by our slope, 1.3897, to get an concentration in our unknown of 0.372 molar. All right, so these last couple parts are just some stoichiometry. So calculate the moles of iron 3 ions and moles of iron in the sample. So first find moles of iron 3 nitrate from the molarity equation. Remember that to find moles, we take our concentration, moles per liter, and we multiply it by our volume in liters. So our concentration was 0.372 molar, and we're told that it was in 100 milliliters. So I've converted that to liters, 0.1 liters, to get 0.0372 moles of iron 3 nitrate. Now, in this chemical equation, we can see that for every 1 mole of iron 3 nitrate, there is 1 mole of iron, right? There's a 1 here. So that is also the number of moles of iron, 0.0372. And then finally, calculate the mass percent of iron in steel wool. So the first thing we do is take the moles of iron that we found in part C, multiply by the molar mass of iron to get our mass of iron, 2.08 grams. And then use this mass percent expression where we take the mass of the iron divided by the total mass of the sample. If you go back a few slides, the mass of steel wool is 2.10 grams. Multiply by 100 and find out that 98.9% of the sample is iron. This result may sound high, 98.9%, but research shows that low-grade carbon steel, or steel wool, typically has only 0.1 to 0.2% carbon, making it almost pure iron.